This work is it's a byproduct. What I'm showing now is not a main work that I do. It's a byproduct of some enhanced oil recovery project that I did back in summer. So I was doing this work and for Gulf, local company, a smaller operating partner and a bigger state company is EGPC. So they have a small equity there, and they're trying to explore, trying to find there are several fields. I'm working on 3 fields simultaneously at the time, trying to understand what it takes to do an EOR project. I think some of the learnings some of the things you see is probably learnings in general. They pertain to the field and also apply in general to a large area. But unfortunately, I don't have a whole lot of data from that field. It's because of the permissions. Moreover, a bunch of sections and the production data won't be very interesting for GS, so it's more a geology story and tectonics and how it matters in a subsurface characterization. That's a kind of story. So it's a Gulf. So what you see in the picture here in the background, it's a rhodized formation. It's a syndips plastics subsurface. That's what you have in subsurface. They're lifted about thousands of feet up on the eastern side of the rift, Gulf of Suez. So these guys, let me use the mouse because I have to be standing there to use the laser pointer. These guys. So these are the rhodized formation. You're looking from north to the south. So that's what it is. And we're going to talk about general stratigraphy and petroleum systems in general, and some field geology. And the accommodation zone, they're actually structural features that are uniquely found in rift basins, oblique rift basins, and how they influence plastic distribution. And also how it affects me in a new EOR project. That's the kind of thing I've kind of driven that. So going back and forth. So I had to go several steps back, see why this is happening and why it's important. So that's kind of a basis of this, going back. This is a Landsat imagery, pretty much. You can see the Arabian Gulf of Suez Basin, Red Sea there, and also this is it's an Oligocene-Miocene continental rift, Gulf of Suez, and it's a continuation of the Red Sea in the northern end. And it's located between Eastern Desert. This port is called Eastern Desert, and also this is the Arabian Peninsula. This is Africa, and this is Sinai Peninsula. It's between these two, and this is called the Gulf of Aqaba. It's a transform. It's not a rift. Nowhere you don't see oceanic crust here, except a very tiny little piece here that happened very late in the rift. So it's a continental rift so far. Of course, this is different again. Now you see a little more detail here. So the reason I'm trying to show this, it's how, if you look at the big picture, you have to go several steps back. The tectonic that you see regionally, they seem to influence the subsurface, the similar patterns you see. That's the reason. Sometime end of the talk, maybe in the middle of the talk, I'll make this connection. What we saw before, this is what is happening in subsurface. If I'm successful at that, let's see what happens. So you have this Afar plume here. It's a big volcanic plume, and it's not proved yet whether a plume caused the chicken and egg thing, but they didn't find anything doming before that. So just before the plume, they have these marine sediments sitting at the same level. So they figured that probably it's not initiation, but definitely somehow around 31 MA, they started this bloom, and reef started going. And another thing you see is these transform falls, the direction of those. That's kind of unique. So it kind of shows the direction of extension. Yeah. And then there's a huge Zagros mounted thrust. You see everything thrusting there. This is a kind of a busy slide, and it's kind of giving you a story what happened. On the left, you have this stratigraphy column, and on the right, you have this tectonic and sedimentary events that happened that shaped the Gulf of Suez. On the left, when you see that, it's only the yellow, the highlighted portion. It's mostly the right side. It's only the Gulf of Suez history. That means something started in late Oligocene. The rifting started sometime around 27, maybe 25, 26 MA, but we didn't see any indications of any rifting on the Gulf of Suez. Can you hear me? It's kind of adjusting the volume there. So, but it's kind of diachronous rift because until late 24, 25 MA, they didn't see any indications of any first syn rift sediments in the Gulf of Suez. So it's called Nukul Formation, Nukul Taiba, and they're volcanic, some red beds and volcanics. And the Taiba, Nukul is the base of the syn rift, the sequence they found, and that's where this tiny little portion. I have pictures of that, but I kind of shielded them for the lack of time. But yeah, when you see that these rifting happen in an episodic fashion, so you have this rifting going on, and there's an uplift and block faulting, and several thousands of feet elevation and these sediments were available for erosion again, and when you notice that during the Miocene time, you have the maximum. This is a Rudise formation is a focus here. That's what the reservoir was working on. That's when the maximum extension took place, maximum carbonation space created in the basin. So, and you can see a whole lot of transcription regression was going on at that time. And the point is, it definitely, the basin is sediment starved, and definitely there were some coarsening up for cycles. Generally, sediment starved. After that, everything, there was an upliftment, and there's a quiet period for quite some time, and during which you have this evaporite sedimentation happening in the Gulf of Suez. All this pink stuff that you there evaporate, they take huge evaporites, and that's a good thing and a bad thing. Good thing is that they seal all the hydrocarbon. That's why we have hydrocarbons there, entire hydrocarbon actually. And a bad thing is you cannot image them. So far I haven't seen any because I'm an outsider. So internal to the company, they may have some right data. We don't know that. I don't know that. But so far I haven't got any decent seismic looking at subsurface. Yeah, geez, this is spectacular, like Gulf of Mexico. No, nothing like that. So hundreds of feet of evaporite. So you can image. Apparently, there's a severe problem there. So and after that, those are the reservoirs I'm working on actually. Kareem, there's Rudise. I'm seeing Rudise. I'm putting a pointer here. Rudise is the reservoir. Karim is also a reservoir. They have clastics and evaporites and carbonates. And Balaam has evaporites and carbonates. And Saudi Arabia has clastics and carbonates and evaporites. And Zayt is mostly evaporites and sealed rocks and some plastics. But generally, the reservoirs are mostly Rudise concentrated in Rudise and Nukul formation. They're pretty clean and beautiful plastics, progradational plastics, high permeabilities. So these are the reservoir subsurface. Anything else from this slide? Yeah, it's pretty much tells a story. There's also igneous activity several times, and you can see that at the bottom there was an initiation of igneous activity a little bit here. This shows the magmatic events here, and there's another igneous activity here. So that gives you the kind of a time frame what's happening in the basin. So this is another regional space picture from a Gulf of Suez. Why did we study this? Before going there, I just wanted to tell that this is why we're doing this. Drifts are because important. They're like 5% of host morphology and 2% of land surface. So, but they have quite a bit of resource there, 10%. So they're important. They're always been important. So, and also they can all these continental plate boundaries started out drifts. So that's why there is so much research in the books. In fact, most of the research comes from these places. Again, this Gulf of Suez in particular, and some other rifts, of course, there's a good connection. So you can establish the connection between tectonic events and sedimentation and hydrocarbon trapping. It's just like it's like a textbook sometimes. When you spend some time and look at it, you can make the connection. Oh wow, you feel so happy about it. So that's kind of story I'm looking at. So it's kind of a lot of theories can be tested, and you can get the results back. So in your lifetime. So another thing you see, these big black lines. These lines are actually the rift boundaries. Those are the main boundary faults. Thousands of feet of throw on them. So it's about 100 feet apart. From here to here, 100 kilometers. I'm sorry. Where this from here, black other one. And this distance is about 30 to 40 kilometers. It varies about that, and this is about 80 kilometers wide. And what other features I'm seeing, you can show this yellow patch here is the field area that I worked on. That's a pretty small area on shore basin. There are three. The whole Gulf is divided into three kind of general, they call it provinces, structural provinces. The middle is called Belayim province, and then the north one is called, I forgot the name, Araba province, I think, yeah. And the bottom one, I think, is Zayt province, and the bottom one. So in the middle, and these big arrows indicate that these are the direction of the dip in these zones, how the beds are dipping in what direction. That means in the middle zone, the beds are dipping to the northeast. That means you got a huge fault on the other side, facing the other side, and these beds are dipping antithetic to that. So, and same thing in the south, this basin, the beds are all dipping toward this side. And these white lines, they're actually transfer zones. There's so much literature. So it's actually, before entering into working this, I had some knowledge, but not a whole lot. I was been reading quite a bit, so I just wanted to bring that knowledge here. So this is called Morgan Transfer Zone, and this is a Galala Zemina Transfer Zone. Some call it Zafrana Transfer Zone. I think one of those names, I think there's a discrepancy in the names, how they're calling it, but generally it's called Morgan Transfer Zone. The transfer zones are basically the areas, broad areas, were like about 10 to 15 kilometers wide, and during that, they accommodate all these stresses somehow, and then the dip changes from one direction to the opposite direction, totally. So that's pretty much consistent as happening. So this is not only happening here, it observed in many continental rifts. So you got these transfer zones where the sense of dip is changed, and then all the motion is accommodated somehow, and the fall through is accommodated. And the fall through in these places, accommodation zones, are minimal at that time. So this is water depths are pretty shallow, 30 kilometers mostly. It's about 320 kilometers long. I'm going to show you another little flight here, which is actually a small ladder plane. It kind of simulates a ladder plane going through on the western bank, and like there's the yellow line, and then it goes to the eastern bank and then travels along that. The reason I'm doing this is because all the geology subsurface is exposed on the rift shoulders. Everything is uplifted, everything is tilted, so you can see it, pretty much walk on them. It's a little laboratory, so I never went there, so I thought when I looked at the Google, this is the best way to show. So I'm going to click this. It's going to start. There's no sound, so you can enjoy. It's going to go a little fast because in interest of time. Can you see this? Oh yeah. So what you're looking at Jebel al-Zayt, it's a eastern western shoulder. Or the black rock, it's our Precambrians, and behind that you have this cinder sediment, is a rice formation. And again, that's one of the very good accessible exposures. Somebody wants to go on a field trip, that's where people go normally. And you go to the eastern side of the Gulf, and there's similar thing you see, but there's more geology over there. There's more, you can actually, more longer exposures. And this is going to go behind that metamorphics a little bit. These are actually basement rocks that are uplifted, and they're all block faulted or reverse faulted. They're not reverse faulted, they're tilted backwards so that these are the oldest, and these are the youngest again. So what you're seeing now is you're driving over is actually pre-rift sediments actually, and these are volcanics, and these are red beds. These are volcanics, and these are Abu Zamina red bed that they call it. They're kind of reddish. In some other place you can see them. And these are again rhodized formation. These are clastics, cindric clastics, and also entire cindric clastics. And you have in some places you have this Thebes Eocene limestone is exposed. These are volcanics again, and these are rhodized. And here you have this limestone exposed called Hammam Farun Mountain. They call it. It's a huge limestone block. So apologies, too fast because it's in the interest of time. It was initially 4 minutes. If you want, I can play it again, but I think you got a gist of it, I guess. So that's something to show, just to impress upon the fact that the geology is exposed on the surface. So even though it's a subsurface work, so that's the best way to show that. Look at the geology in the short time frame. This place is it's a major oil field again. Where this is another major oil field. One of the, in fact, discoveries were done here. Initial discoveries were done here. Ras Gharib is another major oil field. October Trough is another field. July field is over here. So it's another map that shows where the major oil fields are. This is another kind of animation. It's not again. I was thinking maybe I'm going a little overboard on showing the regional tectonics, but somehow I was trying to see. What was the timing when the trap formation occurred? You know, why did the Gulf of Suez stop spreading? And what's the age of these evaporites? And why did suddenly all these evaporites coming in? So all these questions, you know, when you go back and tie to plate tectonics pretty easily, you know, pretty nicely. So I think it was, if you look at this, how this Gulf Suez opened, it probably some kind of education there. It's education for me. So some of you may have known already. At that time I was learning, so when you look at these 31 number came from the Afar Plume, I guess, and they rift started sometime, you know, continental rift initiation happened around 27 MA, and there's already it was opening at this time, but this Gulf of Red Sea was not opening at that time. This is the first time Red Sea opened. So, and initially it opened, there were little volcanics and up front, there were dikes and dike swamps and things like that, but there was no syndrift at 27 MA. And then, hang on a second. And the next one, and after that at 24, the whole Gulf is flooded, and then rift initiated at the northern plate, at the Gulf of Suez. Around that time, and you started seeing the Taiba formation, red beds, and also Nukul formation, and all that. And then around 13 something MA, this transform initiation started. That means pretty much rifting Gulf of Suez stopped spreading, and because the entire stress is transferred to Gulf of transform, Gulf of Aqaba transform. And that took the whole extension stress, and the spreading direction was in the direction. So, and you started seeing the marine deposit evaporate sedimentation in the Gulf and entire Red Sea. And after that, it's continued, and then this is mid-oceanic ridge initiation at the Aden Gulf of Aden here in south, and more volcanics, and then continue, and definitely this is one of the fastest rate of extension. And this, as you can see, this Arabian Gulf started slowly closing. You can see here, and everything. Now this is probably the present time. This is how the present time is. And now it's pretty recent. At this time, you have this some kind of oceanic crust over there, close to between 15 and 16 latitudes. And this is the same picture that you saw before, just to impress upon the different geography and also the physiography of the land and the names. And what you see here is is the direction of these oblique extension. So and then generally the Gulf of Suez is like that, and then all these lines of transform kind of exhibit an oblique rip. That's what I was trying to find. What are the consequences of the oblique rifting in the subsurface? Where is it coming from? This is something in the future again. The future geometry of the Arabian Plate. That's going to happen 10 million years from now. I guess that Bahrain is gone. It's gone completely out of the map. So this is a field on the left side, on the square area is actually the field that I was talking about. It's called Area A. That's where it's not one field. It's an extension of another field. It's a complete all along the shelf. You have this field, but this is the data I have access to working on. So, but I do have access to the rest of the data, but that's not focused at this time. It's too much of a work there. So there are several neighboring fields like Yusur, Shukair, Karim, and Ayun. Ayun is on the further update. Karim is over here. Yusur, this is called Yusur field. Shukair is, I don't remember where it is, but nearby. This area has got about 162 wells at that time. There could be more, but I think I had access to so many wells. Half of them are 1/3 are producing only. The other rest are all non-producers or injectors or something. And this is called the Belayim province in the central area. It's called Belayim province. Now this is a little more detail on the structure. The picture published image, a popular notion of the fault patterns from the region, and also Apache is a big worker there in their place. A lot of publications show this. So now you can see that this fault pattern, again, the same thing. These arrow marks, black arrow marks, indicate that the beds are dipping towards in that direction in that province. So these gray areas are again this called. Here I'm calling it Zafrana accommodation zone. I'm still confused about the naming convention, but I think this is Zafrana accommodation zone. Some call it Abu Galala. Somebody knows better, can correct me. In the south, you have this called a Morgan accommodation zone, and this one. And this is called the center between these two places called Belayim province and Araba province, and here it's called Amal Zayd province. Area is over here. That's where the field area is. As you can see, there are several sub-basins which are all different, even though petroleum system is generally, the source rock is the same generally in the area, but each of these basins have a different kind of petroleum, their own petroleum systems going on, and which way oil gonna migrate. So it's, these accommodation zones are a little bit of focus, my talk now. They're about 15 to 30 kilometers wide. They separate these large grabens. And they're sometimes, and generally, they're more than often, they tend to be elevated in a regional perspective and also local perspective. So they're kind of positive areas. At that time, they were forming. But sometimes they, relatively, because as the basin is evolving, they could go down or up, but they have definitely an elevated topography because of the structural configuration what they have. So this is a little more detail on showing the Gulf of Suez, and these are series of cross sections that you can see. As you can see, these are the pink areas you have here. They are the accommodation zones, and north to that, the beds are dipping to the west. As you can see, this is a huge fault here, and these are beds are dipping towards that way. And again, following zones, the beds go this way, and that's a kind of a general thing. There are several reasons cited for that, but that could be a discussion for some other time, I guess. There are lots of volumes of literature published on those. This is a little more detail on that. It shows about extension, how much of extension is recorded in these things. Apparently, there is a pretty accurate data about these timing and also amount of extension. You can, in the north, you got about 5 kilometers stretching there, and in the middle you have about 14 kilometers. In the south, you got almost 23 kilometers stretching. This is, again, the field area. So what you're looking on the left is one of the wells in the field on the area A that I'm working on. And this well has a core. In fact, that's the only well has a, that's the only core we have. Not much, actually, maybe 9 meters, maybe 10 meters. On the right, it's generalized stratigraphy column there. As you can see, it's just focused on Rhodise formation, Karim, Balaim, and Hammam formations. So basically, it's a Sindrif section. In fact, Sindrif starts from Nukul in the bottom, right from here. So all the way, it's at the beginning of the Sindrif and all the way up to here. So as you can see, there's a prominent sand here. And there are several sands in a way coarsening upward style. And on the bottom you have a prolonged starvation, and not much sand is coming here. And as you go up, sand starts coming in, and again, suddenly everything is flooded, and you got the evaporate layer, permanent layers sometimes, and most of the time you have evaporate layers sitting on the top of the Rhodise formation. And again, the cycle repeats sometime, and again, definitely more evaporate is coming. So, yeah, this is a kind of fits in with the geology. This is Jabal al-Zid. It's basically the area you saw on the left side, on the western side of the Gulf. There's a hill area. It's kind of type here. They pretty much refer back to, because the geology is pretty exposed there. And now you can see that or the geology is pretty close. And as you can see, Rhodise is actually the section where the maximum extension took place with few clastics. And Nukul, at the bottom, you have both carbonates and clastics, depending on where you are. If you are faulted block, you're sitting in good ideal conditions for carbonate deposition, you got carbonates developing. Other places, you got turbidites forming in some other places. And you have this Karim with evaporates and plastics. And again, if you go up, the lime is mostly evaporates and some plastics. And this is same thing you can see here. With this geology, same thing you see here. I took a Google picture. So you can actually, we're going pretty fast on with the lateral plane there. Here we can actually see here. So the basement, you're under the east, and you have, and everything is tilted in the opposite direction. These are the Sindrif sediments you started. These are the reservoir units. And these are mostly evaporates, thin beds of evaporates. They're eroded away, and these are Holocene and Pleistocene sediments after that. Well, that was a big regional picture. We took a little more time than that. The reason we took, because it's just to orient ourselves why. To understand the regional tectonics, sometimes it's essential. And when you go back to this petroleum systems, and this is U.S. estimates about 5 billion barrels in the entire Red Sea, Gulf Coast, Gulf of Suez, Aqaba province. That's based on geological methods generally, not any particular data. But definitely it's a lot more than that. And if you just focus on Gulf of Suez, about 650 mean undiscovered potential. This is again a regional picture of petroleum system. I've got thousands of exploration wells, more than 80 fields are there, and Gemsa is the oldest field that discovered it. And all these major fields account for about 40% of 40% of the resource there. But this is not all, but the future, that's all, they're all under mature fields now. And, the future is going to be on the SNRIP sections, which has not been a focus so far because, there's plenty of oil in other places. So now it's going to be challenging. Now there are a lot of moderate-sized fields. There are multiple source rock. What are the ideal conditions there? You can see the multiple source rock, 3 different SNRIP section, open and restricted marine conditions, the rift blocks, and they're rotated, and they have carbonates deposition, the dolomitization, and the most ideal conditions created by these by the tectonics. And we have a huge elongated gravens and hot structure, so there are plenty of trapping conditions, and there's numerous fields, but they're not big, and also these conditions are repeated because of the rifting process, the inherent rifting process. These conditions are repeated in time, and they get eroded internally in the rift. So there's a little complex geology going on, and you have this. Carbonates and high TOC values in the Eocene or in the Miocene also, and they're good geothermal gradients. Again, a little more fact there. Source rock is predominantly brown limestone. It's a Cretaceous limestone, 2.60 to 2.5 organic carbon TOC. And the creative reservoirs are mostly the Cretaceous Nubian sandstone. The Nubian, the word, they use it very loosely. It's Cretaceous and all the way to Paleozoic sometimes. So it's kind of a... And seals are, again, extensive seals. Evaporate seals are at the top, of course, they're sealing the entire. But internally, you have lots of seals on the drapes on these strocal highs. So, and also a little shale drapes that come on whenever short transgression took place and sudden extension causing flooding event, and you get a thin shale there. So these are the local, the timing of these is important to understand what is sealing what. They change from section to section.
So Sharma,
yes.
Does the brown limestone show on your section there?
Oh yeah. It's a Cretaceous, but it's all the way down. It's a low Cretaceous. Somewhere in this, it's only a schematic picture. So I know it doesn't say which one, but somewhere around here, it's a green color. The bottom of this Nubia, somewhere around here. A little more facts there. Out of these, there are several sources that you can see: brown limestone and the Thebes. The Thebes is Eocene. So these are the dominant sources. In Rhodise also, you got these sources. The reason I'm pointing this out because recently there was some work that thought Rhodise, the entire thing is the source rock is Rhodise for most of these reservoirs. But now, in fact, brown limestone is sourcing most of these reservoirs in SNRIP also. Those are the general ideas, and also mostly you can see it's terrestrial origin. You have some type 1 carbon there, and generally it's a Phanerozoic component, quite a bit of that. The reservoirs are huge, actually. They're very thick reservoirs. Unimaginably thick reservoirs. These are the general pictures that we have seen in textbooks and in numerous APG publications and all. Like these are the classical fields, and you see them. But this is what the picture is. Without a whole lot of seismic data, people just project these what you see in the surface, and based on the wells, you draw these beautiful drawings. And yeah, they all look good as long as oil is flowing. But these things are no more now. I mean, they're drying up, of course. There are some good fields of producing still, but they're a mature stage. But the future is going to be a little more complicated. You really have to dig deeper and see more, image more. Those are the fields these are the most popular fields that we're talking about. Sudir Field, Ras Budrand Field, and also October Field, Belayim Field, and the locations of these are in the south, these all here. These are the pretty major fields. None of these are producing from Rhodise, of course. So now the focus is, that's why they said, hey, we got to look at these CNRIF sediments, we got a much more complex geology. So this is the kind of seismic data coverage that I had. As you can see, pretty big data, but there's not much to it. The reservoir, when you go back, I'll see one section here. It's very difficult to map. This is one of the very difficult maps that we could make. I mean, I didn't map it. The people mapped it for me before I was there. So you can see the fault pattern on the right side. They have some kind of an echelon trend. That's pretty much, the map is towards, northeast towards the north and up to the top. There is a little tendency of these fault patterns to, major faults in the field, to go northwest and southeast. This is a seismic section, and pretty much this is the only seismic section you're going to see. The other, the reason being, I'm not working on this anymore, so I don't have access to other seismic data. This is the only thing shown already, that's why I have no problem showing this. So this is one probably you can give you an idea how difficult to interpret this area is. As you can see at the bottom, if I can see my arrow mark here, this is where the green reflector is rhodized here. So it's kind of hard structure, and this is it's really a challenge to map this. You can map it when you have dense well data in some places. In other places, it's kind of anybody's guess sometimes. But you can still map it, going back and forth, because these evaporites are good anchors. They're really good anchors. You can map them. So when you anchor on Kareem, you can anchor on Balaam, you can South Kareem, you can map rhodized quite successfully. But any deeper, we couldn't map. In fact, I was trying to map Eocene tips, but I was not able to map in this seismic data. Maybe there's other source of seismic data I didn't have access to. So this is generally the snapshot of a seismic data. This huge, extension. This is actually a Pleistocene section on the right side. You see. Now this is a kind of picture of a sanitized, beautified site structure map. It was never like this. It's for the model. It's I had to make a smooth model, so it was a much more problematic looking model surface. This is the rhodized structure top, the rhodized structure top of the reservoir. As you can see, there's it's anybody's guess, it's spilling to this side. So when I was given this data, hey, this got issues. I don't know how to contain this this area because it's spilling everywhere. So yeah, that's how it is. But you got to do this is all you have. But lo and behold, you have another field here, and that's also charged. And there's another field that's also charged on this side, and there's another field that's also charged on this side. But they're different reservoirs. So then this is the interpretation I've got. This is too deficient for me to make a really EOR model. So there's a lot going on, but I'm not seeing anything. So. But definitely it's a step in the right direction. So that's a pretty decent map in structural geology, fault maps that I saw, but it has to be appended. So I did some coherence data and tracking, this Schlumberger we call and tracking, just to do then densify the map. On the left side that you can see, there's a workflow there. Take a seismic data and calculate KLs, variance, and derive and tracking volume from there. You can do that, and you can see that there are a lot more going on here. The fault density is much more actually. It's mind-bogglingly complex, and each of these faults, when you go back and spend some time, there are hundreds of feet of throw on them sometimes. So I made them append some more, densify, beef up the data a little bit more. So we tried as much as we can, and on the colors you see on the side, the bottom right-hand corner, are the existing fault maps. So there are a lot of other faults which are not even attempted, so they're filled later. So now you can see this is the same thing, this existing faults, and now you can see that this fault from Antrac. You can see here the circled areas. So there are little tiny transfer faults here. Here, there's one here, there's one here. So I had a little pushback from saying that, hey, we have not mapped this fault. No, I don't know. I mean, the team, whoever is mapping, they're not able to map these because you cannot map them. There's no surface to map. So they're actually transfer zones that are connecting to huge faults. but you can't really map them. You cannot put a cursor on them. So, but you do see them in a ant tracking data, so you can clearly see them. But they are influencing the production. That's what their contention is, and that's what seems to be. But I didn't know. In order to make an EOR project worthwhile, I thought maybe it's worthwhile. It's worth spending time on these. How we can do that, how we can incorporate those, how they're influencing. So same thing. Again, there is quite a bit of this fault interpretation. Look at that fault is going somewhere else, and the actual fault seems to be going somewhere else. So it's how much you see there, basically. That's all it is. Such rifts you see, these transfer faults, they're everywhere. When you go to other rifts, you can see the Ethiopian rift further south. In the small area, if you can zoom it up, and you can see these things here. This is another area like that. One area like that. These are accommodation zones. The stress is transferred to the next fault from here to here. So if they're dipping in the same direction, they're called relay faults. But there are all kinds of classification. The literature is full of so much research, and there was no way I could finish it without spending a really detailed time and do justice to what I'm doing. So I had to draw some line somewhere. So if you go back and I compare the rest of the, where the rift zones are, accommodation zones are, they're everywhere. So in all these rifts, you see these accommodation zones. And this is a North Sea, and there are how these oil fields are associated with the accommodation zones, what kind of relations they have. I spent some time looking at them. And also looking at the, East African rift system where it's happening now. It's much more newer than these Gulf of Suez rifts. So there could be some answers to that, how these transfer zones influence my geology, right? So I spent some time there. There's some information there. Now you see that I'm going to put all these things together. So now, once I map these, once I draw these coherence data, so these are the field scale transfer zones that I found. That the reason these faults are like that because these are the field scale transfer zones. They're actually the stresses are being shifted from along the strike. The faults are communicating. The stresses are communicating along the strike like that. But actually, there is no physical strike slip motion along these zones. So these are they're being called transfer zones. The time slice is somewhere around here, and actually close to the Rodice top. It's a time slice. So this is approximately the top of the reservoir, Rodice top. That's where the picture is on the right side. So you can see that these faults, there's an echelon on one side, and they overlap, and also they seem to transfer the stresses to the next fault along the strike. But sometimes you can map them continuously with prolonged extension. They are connected, but depending on maybe right now at that time the extension was not enough. There's a gap between those two, and how these gaps influence us, we don't know yet. So this is what you see. So time slice in an Amtrak volume. So they are northwest, southeast trending major faults. And all these faults are mapped again and surgically appended the fault interpretation again. So these field scale transfer zones seem to connect in strike sometimes, and sometimes they don't. Right? And there's no surface to map them. So, and strike slip motion is apparent but previously interpreted. We didn't interpret any seismic strike slip motion in these faults. So if you interpret closely, these are the areas where you can actually see the transfer zones in this field scale. That's how they are. So how they affect us, we still don't know yet at that time. So, but there was a contention that we have to map these faults. In fact, we put an injector here. Suppose if you put an injector here, you may not get anything from the other side. Again, there's a challenge of...
You can't see your finger on the
Oh yeah, sorry. Cursor, I'm using this cursor now. Okay. If you can see these, the question of, hey, why didn't you map? There was a team, they were mapping this. So the management was asking, why didn't you map these faults? You cannot. There's no way. No, some other consultant mapped. No, there's no way you can map these. So the reason is that this is the kind of a geology that you see, but how it influences it, that's what we have to see, how we have to create a best EOR situation model for us. So these are the questions at that time. So, but at that time we said, hey, we cannot map these are transfer zones. They are influencing the geology here. They are influencing when they were deposited, sediments are deposited. They are influencing even now. But how, we're still yet to see. Well, just a brief description of these. And there's all kinds of research going on all these. I went back to dig into deeper into these things. So my time was running very thin at that time. Of course, I'm not charging all the time. I was doing it in my hotel room at that time. So, yeah, these are broad terminology. There are all kinds of classifications. They're called synthetic. They're, they're in the same direction. Antithetic in the opposite direction. And they call it if there is a strike slip motion, they call it transfer fault. There's actually slip motion is there, apparent motion. Sometimes there is no motion. All these faults minimize slip, minimize throw when it comes to the zone, and practically zero offset at these zones. And the other side, they again throw again. So again, and one thing pretty common, they see the dips are the opposite. The bed slip in opposite direction, the fault slip is in opposite direction. This is what they found. There's a whole lot of research for the last 20 years in these areas. So I'm exposed to the blast in the last few months. I kind of know, but I've never spent too much time on it. So, so all kinds of classifications. So where I should go into all these things, I don't know. I mean, I don't know how much time I should spend. So there are all kinds of, then I stopped. All right, Chico, this is so much geology into so much structural geology, so I don't think I'm going to lose my client here. So then this is what is happening there. So all kinds of, whether you want to incorporate, how much you want to incorporate in the modeling, we don't know yet. So I'm not going into these details, but that's so much of geology is going on. Then I found one research, very beautiful, in fact, the experimental work, and fantastic. So when I looked at it, it's a 4D evolution of brittle fault, exactly what I was looking for. I was so happy to see this. So this is an experimental model. It's a simple experiment and can explain based on the pictures. They pretty much tell you what it is. So it's supposed to simulate about 1 to 10 kilometer thickness of brittle deformation. So and then and also you can actually vary the extension perpendicular angle between the direction of the extension, whether perpendicular or an oblique to the rift. You can do that, and also you can have or not have the basement weak zones. Apparently, most of these transfer zones are a function of the basement weak zones, and that's been quoted in every page. So, but nobody proved it. Yeah, all kinds of theories. So, geologists are welcome to argue. But this is kind of undeniable when I look at it. There's a strong influence of basement weak zones, and they can pretty much predict the direction of the fall and on all these, and simulate all these transfer zones in experimental models. So basically, they're rubber sheet in the bottom. You got aluminum plates in the bottom. They can measure the amount of extension and then record it and see the sand, multicolored, double-colored sand layers, grain sand. Basically, they follow pretty much dry sand, same 30-degree angle faults. You can see pretty clearly on those things. So you can actually change the extension direction and the angle of to the rift axis. You can do all these things in this experiment. So it's too much to go into the detail, but you get a sense of it. So basically, lab work. So and you see these pictures, fantastic looking pictures when you look at them. These are transfer accommodation zones. There are all kinds of variation, but I'm only showing two here. So this one is with an oblique extension, like the rift axis is towards like that, and the extension is somewhat oblique. This is almost simulating a Gulf of Suez rift. So when you look at these, you take transects along these various places, and this is the geology. This is how the Gulf of Suez geology looks. I was impressed, and I look at it and say, wow. Then I'm looking at it, lines of section, and see the bed slip in opposite direction, like that, and suddenly there's a small subbasin developed. There's a subbasin developed here. In the middle, you have a relatively higher zone, and there's an accommodation. There's a little white square. It's an accommodation zone. There actually stresses are being transferred from one direction to other. So And they proved that these accommodation zones with a moderate extension, they're positive structures. So that means always these accommodation zones, they're positive structures, which has a lot of bearing on the sedimentation. They act as a drainage dividers, they provide source of sediment, and they act a hell of a lot. In fact, the sediments pinch on them, and they once solidified the shale is in, and that is actually sealed. That reservoir section is sealed and gone, subsided, but that's intact and sealed by a marine shale. And again, rejuvenation, it may not affect, unless it is exposed and eroded, it may not affect. So you have hydrocarbon in place there, actually. So these are the things I was thinking, you know. So relatively elevated accommodation zones are a result of extreme extension, oblique to the rift axis and influenced by rejuvenation of basement weaknesses. These accommodation zones act as sources of sediment, drainage divides, allow thousands of feet of sediment accumulation in basins on either side, and also enable lateral seals. So this is just a summary of the huge paper that I was reading that kind of interesting to me, and I brought this up, and I used this as an analog to why this could happen. And also there's another occasion where here your basement faults are influencing your rifting process. Here one thing about this one is the accommodation zones are parallel to the direction of X. And this is kind of a lab model. In reality, there are a lot of heterogeneities in the rock, natural rock, so you have to take that into consideration. But despite that, you can see the geology that is developing on the right side. It's spectacular, and it pretty much simulates what I saw in the seismic in the field, and a pretty good match there. So I was impressed. The point is, this research is there in the books. I don't think I've seen anybody using this for any actual work to make money. So let's call them astronomers or whatever, but it's a useful work. So we have to use them. And, that's something I realized it. So usual field as zones are very similar to geometry to experimental models, and relatively narrow zones seem to have been influenced by rejuvenation of pre-existing basement offsets. No strike slip faults are observed, so it's not a measurable strike slip there in these things. This is an example of orthogonal extension. That means basically the extension is happening perpendicular to the rift axis, and the previous one is oblique to the rift axis. There are innumerable models, entire scale of, based on the experimentation, you got a whole range of. So these things I like, the pictures, when I looked at a small postage stamp of the field, it's kind of amazing to see what you see in the regional context, in the plate tectonic, the major accommodation zones. They're kind of repeated in a field scale that you can only see in the ant tracking data. You cannot normally see them. This is another kind of summary slide of these accommodation zone concepts. So high relief. Am I good at time? I think I'm pushing it. Okay, yeah, I'm going to wrap it up 10 minutes. So on the left, you have high relief accommodation zone. On the right, you have this low relief accommodation zone. On the left, I think that's what is happening. You got a pretty much elevated portion accommodation zone that becomes source of the sediments, all kinds of things I said before. They're influential. Low relief, I do see those things. In fact, the Morgan accommodation zone itself is a low relief accommodation zone. You can actually see a structural low in the rhodized top. There's another field separates down and further south, and the user field is another separate field. That's actually a low relief accommodation zone. In fact, they were not able to tell me, oh, you don't go beyond that. No, that's not part of the field. That is a field. That's actually spilling into it. Why is it not spilling there? The structural law. So then I went back and looked at this is the reason. Another stratigraphy zone is a pay there, not rhodized. So. Then this is a general big picture of a kind of conceptual how the sedimentation could be happening in in a rifted basin with accommodation zone, as I said in the beginning. So this is a positive area here. There could be turbinates forming. You got a fan deltas forming on the scarps on either side, and once the sediment enters the basin, probably it goes along as a turbidite in the middle, and it goes along the Gulf Coast in the deep water sedimentation. And you have all kinds of environments within 30 kilometers of distance. So go figure. So it's not a whole lot of big area. So it's kind of interesting when you see all this. Evolution, again, the sediments, they come as fan deltas initially, and they become turbidites in the deeper aspects, and they're controlled by the local topography. Those things can be, if you have enough data to map, probably you can map it pretty neatly, but because of the, without this understanding, it's very difficult to make a model and to understand how the sediment is distributed, because you cannot see. Imaging is very poor in that place. So you have to have a priori model in your brain to how things could happen. And again, this is just a model, generalized, very generalized facies model I use sometimes, like axis, off axis, and margin when to model. When you model these facies models, you got to have some kind of geographic direction and all that. Geometries, what kind of geometries are reasonable in this kind of environment. So I use this as a concept. Another petrophysical, just one slide. We had only one core that actually, based on that, we could predict the permeability of these rocks. So after the cleaning up, you can get that curve. So this is another sequence stratigraphy. I'm going to go fast on these things. We're pushing. So this is the region. This is the focus area where the blue area. That's the region where maximum extension. You can see that on the right side. So that's where most of the sediments are deposited at that time in the thing, in the syndic sediments. So predominantly they are mostly high HSTs and TST. That means high sand system tracks and transgression system tracks. Usually you see generally a coarsening upward cycles in these several spells of those in these situations. So that's what based on the analogs and based on other bases in the war. So basically ion formation, upper rhodized formation is here. We got 3 distinct parasequences I found. So, and this is a kind of a comparison of idealized coarsening upward sequence somewhere in the world. This is what is happening in a rift kind of situation. It is actually an example, a paper from Brazil offshore onshore field. On the right side, you got this our well, and it's pretty much a very nice comparison there, coarsening upward cycles, several cycles, and we got our model there nicely. So. So we got these 2 previously mapped, and in fact, they were the biostratigraphy data I used it. So they kind of nicely match that cycles. This is another little detail. On the left, you have these 2 analogs I found in Brazil, RTJ Basin rift system. It's a pretty well documented study there. They're more coarsening upward. On the right side, you got another southeastern Brazil example from lacustrine all the way delta to the fluvial and evaporites. So these are the cross sections. You see the present structure cross section. The blue line, blue is a flooding surface that you see. You can map it. It's a present structure now, and I kind of when you flatten that and you start mapping it, and you got these unconformities. Made my correlations based on that in my mind. How many unconformities I have, how many spells of uplift I have, what kind of sediments I'm getting, what kind of cycles I'm talking about. So the previous correlations were sand-to-sand correlations. I junked everything. I kind of removed it out of the door. So I started doing the more genetic kind of correlations. So that way, from sediments coming from to the northeast, going to the northeast. So you got multiple progression sequences that's happening, being deposited. There's another cross section. By the way, these dots you see there are hydrocarbon or no hydrocarbon in those wells. In fact, started off from there. So there's another cross section, similar line, but little variance, because I had to make around 20, 30 cross sections like that, because some of these wells don't produce no hydrocarbons. I have to find out what block was higher at what time. And these are all multiple series of like piano keys. They're going up and down during the rifting process. So we had to figure that out. So why the oil is there in some place. So this is similar, again, concept here. Again, progradation happen, unconformity, and multiple cycles of progradation. So down the road, further down, it's not the same sand actually. One point is that the sand towards on the southwest side is not the same sand. Is on the northeast side, so there's much younger sand. There's something to point out. So you cannot just draw a line and try to flood the reservoir. So you had to go back to the genesis of it. So similar, it's more of a strike section. Most of the majority of the field production is onto the south, as you can see here. This is where most production is, of course. And if you go strike section, that's how you have a high continuity of the sands. You can see. That's a flooding surface, and it evaporates on the top. That's a Karim rice formation evaporates. So that's a flooding surface again. So this is how I kind of ended up making, and then made a model and look at and once you see that these transfer zones, they're actually structurally elevated at the time, and I found it automatically came out like that. And somehow they thicken in the base, in the space between these transfer zones. So basically you have dipole centers between the transfer zones, and up-dip pinching towards the transfer zones. And in fact, initially it was a one sand kind of dilemma there, where there's a water above the oil in some zones, and that's why we had to divide the zone. So, so this is what we found. The significant point is these transfer zones have some predictable relations to these isopac thickness of these zones within this small zone. We're talking about just 300 to 400 feet of section here. So. Similarly, another section, that's how it is. We found it. The section is deepening in between the transfer zones. The transfer zones, it's structurally higher. These are the conclusions. It took longer than I thought. Poor subsurface image. We had we don't have a best image. If that's the best image we had. So, but that's probably not a constraint at that time. So, Antrac volume really supplemented the complexity, brought the heterogeneity that's needed to do a newer project. So in a newer project, you got obligation to know more about the surface, honor everything you know in subsurface. So that's something you cannot ignore what you know already in a newer project. So anchoring well correlation biostratigraphy, using biostratigraphy synthetic sequences, and evaporates help, and also applying principles of sequence stratigraphy, enable good maps. And I think you can model what you cannot imagine, what you can image. So you really have to have a good understanding of the geology, spend some time up front. So you don't have to have a best estimator, but still you can work on it. It's somewhat genetic approach is essential in the river basin because it's predictable. It's an ideal situation, as I told you. Gulf of Suez it's kind of like a textbook. If you spend some time and you understand, you can relate a lot of things together and make up come up with a good geology. This is what we should be doing. So you got to know the engineering work, what engineers do, and talk their language. But what you bring as a geologist to the table is more important, actually, than being a geologist. So that's what I do. So I think that really helped at that time. So I thought it's a good story to tell. So thanks very much. Intention made by engineering community. And we turned out, no, it's not. It's not a production barrier. Depending on where the reservoir is, for example, first of all, stratigraphic correlations were in that particular reservoir, yes. In the lower reservoir, yes. In upper reservoir, the transfer zone in one particular did not influence the younger reservoir. See what I'm saying? So depending on the stratigraphy, so it's a timing of the formation of the structure high at that time, so that deposited sediments on either side. But yeah, yes or no, in some places yes, in some places no. So in the field I saw, in the transfer zones, the contention was to place the wells on the same side, for the injector wells on the same side, assuming there's a transfer. But we did not see any indication because we found hydrocarbons way further north also. And somehow they're being drained. Production data tells us that they're being drained. So that's some inside information. So.
Linda has a question.
Oh, wells first. Oh, this is actually a newer project, so I will start with the production data. So basically look at the production data, what production is telling us, because engineers know a whole lot more than what geologists know in these places. So, so we look at this data and see what the production, then we go back to dig into why it's happening. So of course the wells, yeah. The seismic comes later, kind of like a postmortem.
Okay, well, you certainly have gotten me an appreciation of the complexity of this small little corner of the world. Here's your Rattlesnake limestone, which I'm sure you're familiar with, from the unknown quarry west of Austin.
Confidential.
So thank you very much.
Thank you.